Hi everyone, I'm Xuhai. It's my great pleasure to present our work, Leveraging Collaborative Filtering for Personalized Behavior Modeling, a case study of depression detection among college students. Depression is a common but significant health challenge. The percentage of the population with depression has been increasing in the past few years, especially for people aged from 16 to 25. More than 10% of young adults in the US had at least one depression in the year. There is a growing realization that data collected from everyday devices can help us to understand the relationship between people's daily behaviors and symptoms of depression. However, most of the prior work on algorithms follow a one-size-fits-all approach, building one model for all users to detect depression. As an old saying goes, no two snowflakes are the same. Similarly, no two persons are the same. Such an approach de-emphasizes the important fact that individuals behave differently, leading to lower model performance and a limited population-level interpretability. Training a personalized model on the user's own data is a straightforward solution, but requires a large amount of data, especially ground truth labels. However, mobile sensing studies, especially those focusing on mental health-related issues, have a lot of person sensing data, but usually very few labels. Our novel insight is that labels drawn from relevant people can help to make up for the fewer labels, using a method inspired by collaborative filtering. A user item matrix is a typical setup for a collaborative filtering-based recommendation system with user ratings for items like goods or movies. New item rating can be suggested based on a similar user's rating of a content a user has not seen. Our approach is analogous. Instead of items, each column is a feature calculated from passively sensed user behavior at a specific time. The final item is a label, in our case, the user's score on a depression symptom scale. When a new user comes in, we can leverage the same user similarity score developed for the collaborative filtering to identify a specific group of users to predict the rating, which is depression score in our case. In the next few slides, I will introduce our pipeline. We collected data from a wide range of sensors such as Bluetooth, screen, GPS, and extracted a number of features from the raw data. Each behavior feature forms a time series, which we define as a user behavior profile. Then, we calculate a behavior relevance matrix. People who behave similarly and who behave oppositely will have high relevance. Thus, the matrix uses square of the Pearson correlation between two users' behavior sequence. We then conduct a feature selection process on the training set. For each feature, an inner leave-user-out loop is used to find the most important and stable features. When a new user comes in, we first calculate their relevance score against the users in the training set. For each selected features, we choose the training users who have high behavior relevance scores. This leads to a personalized training set for each new user. We assign label score -1 for non-depression and 1 for depression. Then, we use the relevance scores as the weight to aggregate the training users' label scores. A score greater than 0 leads to depression, otherwise it leads to non-depression. This gives us an intermediate classification output for each feature. Finally, we use majority voting to merge these outputs into the final classification. We evaluate our method on two independent datasets. The ground truth was collected via a well-known depression survey BDI-2. Our goal is to detect whether a student has at least mild depressive symptoms. The two datasets were collected from Carnegie Mellon University and the University of Washington. Each dataset has around 100 users, and based on the BDI-2 outcomes, around 40% of them reported at least mild depression at the end of a semester or a quarter. We apply our method to the datasets, and the figure shows the accuracy and prevalence score of a single majority vote baseline, a state-of-the-art algorithm, and our method. On the left, our method achieves over 5% higher accuracy score and prevalence score on the CMU dataset. We replicate our pipeline on the UW dataset and achieve about 3% advance compared to the state-of-the-art, as shown on the right. These results indicate the effectiveness of our method. Moreover, our method goes beyond just having better prediction performance. In addition to building an accurate model, we need to know more about the context to better interpret an individual's behaviors. To enable personalized interpretation, we extract personalized behavior rules that can capture behavior differences between users with depression and the users most different from them, which means it's the user in the training user group that had a negative correlation. We discretize features and employ association rule mining to find frequent behavior rules. We identify contrasting rules that have identical X and different Y. The example here shows a pair of contrasting rules, where the X indicates users spent a small amount of time at social places, but for Y, a user with high depression had more disturbed sleep, while users in the contrasting group slept better. We plan to seek collaboration with domain experts to further study how this personalized interpretation can be used to support personalized therapy design. To summarize, in this paper, we present a new approach to leverage behavior relevance among users for personalized classification on mobile sensing data. We apply our method to depression detection among college students. Compared to the state-of-the-art, our method has significantly better performance. Moreover, we demonstrate that our method can generate personalized behavior rules for students with depressive symptoms. With that, I'd like to end my talk. Thanks to my wonderful team for doing the great work together. And thank you all for listening. I'm happy to answer any questions.